Thanks a lot for the introduction and also for giving me the opportunity to share my research with the conference. And I'm especially honored. Last night, before giving the keynote speech, I already have the award. so it's a very interesting and successful conference. So the talk today is on how to share when data is encrypted, you upload it to the cloud. How do you have privacy preserved sharing with other users? Well, we are in the era of the big data, so that's why we have the big data conference. As data is being generated at unprecedented speed and volume, the challenge is really you have to store the data in a reliably, in a sometimes free and efficient manner, right? And that has been the business driver of a lot of cloud storage service providers. We just take a look at some of the big ones. Dropbox, today it has 400 million users, which is a huge number, right? Finland has 5 million population, so this is 400 million. Microsoft SkyDrive recently changed into OneDrive. I don't have the most recent number. It has 250 million users. And Google Drive, within 2 years, it amassed 240 million. iCloud, by the July of 2013, within 2 years' time, 320 million. So the question is, when you upload your data to the cloud, how about your data security and privacy? So how are they doing as service providers in protecting our data privacy? To answer the question, we need to look at their security model, because when you design security systems, the most important is look at the security model. What is the assumption? Right? In the current cloud service providers, their security model is that the assumption is we trust cloud to perform user authentication. We trust the cloud to perform access control for the user. And also, we trust the cloud to keep our data confidential. And thirdly, implicitly, we also, the model also assuming user is trusted to do the correct thing. But sometimes most of the users are ignorance. And a lot of security breach because of the user ignorance. Well, let's look at those three aspects: user, authentication, and data confidentiality. So let's start, look at the user. Well, human being is the weakest link. And most of us do not know what is going on in the system. So if we take the last year, the Hollywood celebrity nude photo hacking incident, the photo was exposed because when they took the picture, the photo was automatically uploaded. They may not have the intention to upload the photo to the cloud, but it was the device was configured to do automatic uploading without their knowledge. And authentication. Most of the incidents, security incidents, or hacking, start from user authentication. So same is true in cloud storage services. There are many problems with password-based authentication. And after that incident, some of the service providers start introducing two-factor authentication. But two-factor authentication has its problems too, cannot solve all the problem. The Hollywood hacking was the hackers, they had access to Apple's password reset information, right? So the reset information essentially asks for users what is the name of your pet name, right? What is your first car, right? So those informations you can go to their Facebook to get the information, right? So this is on the user part. And also the authentication. The next one is, can we trust the cloud service provider to keep our data confidential? This is what some of the famous people remarked. Tim Cook, the CEO of Apple, he said that when an online service is free, you're not the customer, you're the product. So there's nothing free, right? And Bruce Schnell, he's the godfather of security. He wrote the big book, Red Cover, Applied Cryptography. He started his own company on security management. The first security company take up insurance. So if the client get attacked, there's insurance to cover him. So what he said is that these vendors, those big players, they are becoming our feudal lords, and they make security mistakes. In addition, they perform data mining to make money, and they may turn us into the authorities. Well, the last one, the next one is Revest, the RSA algorithm, the first inventor R. Cloud computing sounds so sweet and wonderful and safe. If we're calling it swamp computing, you might have a better idea, right? So in the cloud, as far as data storage is concerned, the correct model should be, we cannot trust the user will perform the correct operation or system configuration. And we should not trust the service provider to perform user authentication in a secure manner and to perform correct access control. And of course, we don't trust the cloud provider to keep our data confidential. So this is the assumption, right? So under this assumption, how to have storage service? Well, in a secure manner. The solution is use encryption. Because by using encryption, only the data in encrypted form, only the ciphertext will appear in the cloud. So even the cloud is hacked, is broken, even the authentication system is compromised, your data stays in encrypted form, will not be leaked. And when the data comes to your computer, locally you perform decryption. So that is why if we take encryption, we don't have to trust the cloud to perform access control. We don't have to trust the cloud to keep our data confidential. Right. Well, the problem with encryption is, before that, some of the service providers today, they do encrypt our data. So when the data is uploaded, the service provider keeps the data in encrypted form. It's already encrypted. They do this. The problem is the service provider has the key. They can decrypt. So if a hacker broke into your account, he can also access your data. The cloud provider will also perform decryption. So this solution is not so effective. So what we are advocating is user ourselves, we perform encryption and decryption, not the service provider. The question is, when data is uploaded in the cloud, we want to share with other people. But how do we share with other people when data is encrypted? Well, the traditional approach, we could use public key solution. But public key solution, the shortcoming is that it is a one-to-one encryption system. So I know your public key, I encrypt the data, you are the only user who can decrypt. But if I want to share my data with 100 people, so I have to perform encryption 100 times. So that is, in that sense, is not scalable. And of course, symmetric encryption even more not scalable because we need certain techniques to do key distribution. So in the crypto community, the new technique invented for this kind of application for sharing of encrypted data is called attribute-based encryption, ABE. So it's a new type of public key cryptographic system. The system was invented, the concept was invented in 2005. And in 2006, there were two kinds of ABE were introduced. The first one is Ciphertext Policy ABE, or CPABE. So CPABE is very similar to role-based access control. So we want to access our encrypted data in the cloud. We specify certain roles. Here is specify certain attributes of the user. The second type, Key Policy ABE, or KPABE, is more for content-based sharing. So I have the data, I perform encryption. The data are embedded with certain keywords. And I want to search those documents with certain keywords. Then you use KPABE. So today, I will just focus on CPABE. So this here is how CPE works. Maybe I just show the system, use the picture. So in CPABE, there is an authority which we have to trust. For example, the authority could be a server in your organization. And that server will issue secret keys to users. And each user has a set of attributes. So for example, Charlie has the attribute, his identification number, his affiliation, and his position. So similarly, Alice, her number and affiliation and position. So you can have many other attributes. And based on the attribute, the KGC, Key Generation Center, issue secret key. So secret key are bound to your attributes. Attributes are your capabilities, your credentials. Well, the data owner, to upload data to the cloud, the data owner will perform encryption. The encryption is using, here we call it a public parameter, PP, just like public key. So every user in the organization just need to know the PP, public key. And he can use this as the input, use the message, maybe electronic medical record. And A is the access policy. So when you encrypt, you define an access policy. So my access policy is anyone with this identification number can decrypt the data. Or anyone working for the general hospital at the position of a cardiologist can also decrypt the data. So this is the policy. Right? And the ciphertext, the policy are all uploaded in the cloud. when the user wants to access the data, so if the attributes satisfy the policy, the data can be decrypted. If the attributes does not satisfy the policy, the decryption will be denied. So this is essentially the CPAB. So for example, Charlie has the identification number satisfy, so it match. So he can decrypt. Alice works for the general hospital, cardiologist, satisfy these two leaves. She can also decrypt. Other users, you do not satisfy the policy, you cannot decrypt. So why we are saying this is a good approach? It is a good approach because it performs one-to-many public key encryption. So as a data owner, you just specify the policy. You don't have to specify each and every potential recipient of the data. You just specify the policy based on the recipient's attribute. So one encryption, not many encryption. And the policy is flexible and expressive. So it wants to have many policies. The language must be expressive. The CPAB support only Boolean algebraic combination, and or. Right? So which is fairly expressive. The last aspect is, by doing this, we do not have to trust cloud to perform user authentication. You can still have user authentication, but for the purpose maybe of charging the user, but not for keeping the data confidential. And the cloud does not have to perform access control. The access control is built in mathematics. So it's only when your attributes satisfy the policy, the mathematics will decrypt, will work. Otherwise, it won't work. So this is the basic solution of using CPAB to perform access control of data in the cloud. Well, let's look at the access policies. What can it do? So it can perform a lot of functions. So for example, the access policy can support integer comparison operators. And the support of the operator is not direct, it's by indirect support. For example, so if we want to compare a time-related attribute with a Unix time, then we have to add 32 leaves to the policy. So it's a sequence of binary comparison. We can do the time comparison. My key expire date is larger than certain time, because we need to add 32 leaves to the tree because Unix time is 32 bits. And the problem with this is the decryption operation is linear to the number of leaves you have. So the more leaves you have, it takes more operations. The operation is the bilinear pairing operation. So bilinear pairing operation, well, even people working in the crypto community, most of us, we don't know how bilinear pairing works. We just use it. We use the property. All right, it's a very complicated mathematical concept. But it has, based on this, many new crypto systems have been designed. And so each node corresponding to one bilinear pairing operation. That is expensive. One pairing operation is 3 to 5 times more expensive than RSA decryption. Right. So just some numbers. Suppose we have a policy with 100 leaves, this kind of leaves. In a mobile device, it will take 30 seconds to decrypt. In a PC, it will take more than 3 seconds to decrypt. So which is clearly not acceptable. Well, so what we did is you cannot bypass the decryption. It's not possible, right? So what we can do, we propose to do, is that we let the decryption be after-sourced. So as a cloud server, you store my data, and you perform decryption on my behalf. But after decryption, you cannot get my data. Because if the cloud, after perform decryption, get my plain text data, that defeats the purpose of the encryption. So what we do is we split users' secret key into two parts. So one part is called transformation key. The other one, decryption key. The transformation key is given to the cloud. So when I want to download a data, a message, the cloud will use the transformation key to perform 99% of the operation. And those operations are public operations. So even you know my TK, even after performing the operation, you cannot get my data. Right? And so this transformation transforms the original ciphertext into a simplified ciphertext, such as R-gamma. The R-gamma decryption is only one exponential operation is enough. So it comes back to this give to the user using DK to perform the final stage of decryption. And so let's see what are the next features of this solution. Number one, it is secure. In security, the minimum requirement today for encryption is the so-called semantic security. So semantic security means if I only have two messages, I perform the encryption. Right? You give me the ciphertext, I cannot tell which message is encrypted. So even a message is 1 bit, I cannot tell which message is encrypted. That is semantic security. The second one is verifiability. So we let cloud to perform decryption for us. But how do we know the decryption is correct? Maybe the cloud is performed the decryption yesterday. Today, the cloud is lazy. Pass us the transformation yesterday, not the newly computed transformation. Right? So we can guarantee that the decryption is indeed correct. Right? That is verifiability. The third one, the major objective is to increase the efficiency of the user. So how much efficiency can we get? Well, this is the ABE decryption, the standard ABE decryption, using a mobile device on a PC. This is the number of attributes in the access policy. So if we have 100 leaf in the PC, it will be around 40 seconds in the mobile device. The PC around 4 to 5 seconds. Right? But with the ABE, verifiable after-sourced decryption, on the user side, we can reduce the decryption by a significant amount. So using a mobile device from 4 seconds to reduce to less than 0.1 second. And on the PC, it's 1% of a second. So essentially, we can solve this decryption efficiency problem. Well, the second one is in security systems, for example, smart card. Okay, we have a smart card, we make the smart card tamper-proof. But if you try to tamper the smart card, it self-destruct. But there are side channel attacks based on the power consumption, based on the time the decryption algorithm operates. We can deduce the secret key inside the smart card. So the same kind of careness we should apply to other security systems. Same thing here. Well, the data is encrypted, but the policy is in plain text form. So data protected, how about the policy? Can the policy leak certain information about the user? Well, in this example, maybe this is an extremely example, I intentionally put it here. So we are encrypting electronic medical record. And we have the user's identification number, right? So you just look at the access policy. Probably you can speculate this particular user with such an identification number is suffering a heart problem, because it can be is cardiologist in the hospital. So this means what? This means the access policy in certain applications can leak lots of information. Data encrypted, access policy not protected can leak information. Right? So our second effort is to solve this problem. Can we completely hide this access policy? We have the ciphertext. We maybe also encrypt access policy. Then the problem is, how do you decrypt access policy? Right? And also you have the efficiency problem. You have so many ciphertexts. Every access policy you must check. So it's not efficient. So our solution is to split the access policy into two parts. The one part is the attribute name. So we split attribute into two parts. One is the name, generic name. For example, social security number, affiliation, occupation. So those generic names, they are not so sensitive. They don't leak much private information. And the second part are the attribute values. The values are the ones which are sensitive. So for example, the social security, the real number, the hospital, the cardiologist. So our approach is to, after splitting in the tree, we hide those values. We make the name in clear text. So this is just one straightforward approach. But if we just do this, the system is not secure. It suffers from dictionary attack. The adversary can just try different attribute values. He can guess the value. And to defeat dictionary attack, we have to use a composite order bilinear group. And composite order bilinear group is more complicated. So that is the advantage of the solution. It introduces more computational cost, because we use the composite order bilinear group. Well, the last issue I want to mention is the key or user revocation problem. When a user is in the organization, he has a set of attributes, he has a secret key. But that secret key will stay with him forever. He can always keep the secret key, right? Because it's just a data structure. And when user leaves the system, he can still use the key to decrypt your data. When the user's key is compromised, is get hold of by hackers, the hackers can access your data. So when user leaves the organization, when user's secret keys are compromised, we have to revoke that secret key of the user. So in any cryptographic systems, key revocation is always a headache. But it's essential. We must do it. Well, the solutions. So before I talk about the ABE solution, I want to just talk a little bit about the solution for identity-based encryption. So identity-based encryption is invented by Deng and Franklin, right, in 2001. So this was the the starting point of the attribute-based encryption. Yeah. So initially, it's identity-based encryption. Identity-based encryption means if your email address is your public key. So if I know your email address, I can send you an encrypted message. You can decrypt. So that is identity-based encryption. Well, so I talk about this because this concept is easier to understand than ABE revocation. In the identity-based encryption, is also face the same problem. The user leave the organization, must revoke his or her secret key. Now, the approach in the original paper they proposed is to concatenate your identity, for example, your email address with the time, maybe with the time of the day. So every day, early morning, the server will generate a new secret key for you. And that secret key corresponding to your real identity concatenate with the day, right, with the date. And so in this approach, if the user leaves the organization, I will not issue you the new private key, the new secret key, because your public key, your identity changes every day essentially because of the T. Well, the disadvantage of the solution is the key server must have secure communication with users every day. In the early morning, I must do this secret key distribution over a secure channel. Right. The second major effort is to have, this is the RIBE, is revocable IBE. It's a tree-based approach. So in this approach is trying to make this communication over a public channel instead of a secure channel. So yeah. So in the second approach, but each user must keep a large number of secret key values. The number is log n. N is the number of users in the system. So the user keeps large number of secret key values, and the update message are public. So the KGC still talks to users in the morning every day, but over a public channel. But in trade-off, the users must keep a large number of secret key values. And we have this is a new solution we're going to present next month in Euthorics. Yes, September. So in this solution, so what we can do is it has two features. One feature is no communication between the key generation center and the users at all. So to revoke the user, there's no communication. The only communication between the KGC and the user is when the system set up, I issue the secret key. After that, stop communication. And to do the key revocation, is only the center talks to a public server. Maybe this is an email server or the cloud server. And to have public communication. So send some public data to the cloud. The cloud will just do some public operation, then the user is revoked. Right. So this is so far the best solution we can have. For this, but this is for identity-based encryption. For the user revocation in ABE, ABE is a bit more complicated. The revocation could be due to user leave the organization, key being compromised, or user's attributes change. Maybe certain attributes are taken away from the user. Maybe certain attributes are given to the user. All those will have to initiate the key revocation process. So the approach is similar to IBE, very similar. So the server broadcasts key update information, so that unrevoked secret key can be updated. Can be updated to decrypt this kind of ciphertext. So every time you encrypt, you must incorporate the current time t into the ciphertext. So only when the unrevoked user, they have the capability to perform decryption. When the user is revoked, he cannot decrypt this kind of new ciphertext. But in the cloud, the complexity, there's another dimension of complexity, which is after the key update, the system only protect future data, only protect current data and future data, not protect data encrypted in the past, which are already in the storage. Right. So we have to solve this second problem. And this second problem was, in a way, was solved by this paper, by Shanghai and Waters paper. Those two, Shanghai and Waters, these are the original inventor of ABE. Well, in their approach, they invented a technique. It's called ciphertext update. It is also called revocable storage. Right? So you want to the existing ciphertext you encrypted in the past, you update those ciphertext to the present time, so that the revoked keys are not able to decrypt them anymore. So this is a technique, but it has certain restrictions. The update is performed by the cloud. It's all public operation. There's no secret operation being involved. There's no data leakage. But the other approach is we can use our verifiable after-source decryption approach, a very simple solution. So remember our solution, we split a user's secret key into a decryption key into a transformation key. Well, we can simply give the transformation key to the cloud server. If the user is revoked, I will not do the transformation for you. That's all. Right. So very simple, elegant solution. The catch is that the server is assumed to be semi-trusted. If the server collude with user, then the solution will not work. So that is essentially all I want to say. There are other research in this area. For example, how to prevent a user selling his private key for money, because my private key is not bound to the user. It's bound to a set of attributes. If that private key is compromised, all the user with the attributes will be affected. So there are such solutions available also. There are quite a few other solutions, but the ones I mentioned here for the after sourcing decryption for efficiency, for using the partial hidden access policy to protect the privacy of the access policy, I think those are the essential things we have to do. And also, user authentication, more or less, we have a good solution available. I think that's all I have. Thank you very much.
So first, thank you for your talk. I would like to know, the data owner has to trust all the KGC that distribute key.
Yes.
From different organizations, possibly, because it might be a problem, right?
Yeah. So it's a very good question. The question is that we have to trust the KGC to keep our secret key confidential, right? Well, it depends on the what is the application scenario. For example, if organization wants to outsource data storage to the cloud, the organization should maintain the server, the KGC server. But if it's your own data, individual basis, you do the outsource, you can run the KGC yourself, right? Yeah. And there are also research to split the function of the KGC, such that when KGC gets compromised, the system's still secure.
Yeah, thanks for your talk. I was just wondering, like you gave an example to start with Dropbox, Google, and so on and so on. But with this kind of key generation server and so on, how will it be feasible for like general user to use it? Like I have a Dropbox app in my mobile, I can use it from my PC and so on. So how will who will store my keys in these multiple devices cases? And for the normal user, I think this running its own key generation system is not feasible. So what's your thought on those?
I'm not very sure if I understand you. What you're saying is that a user have multiple devices, and how do they perform encryption and access control? Is that the question? Yeah. Well, if the user has multiple devices, you have to replicate your secret key software into multiple devices. Right.
I think the other part of the question was whether, because you have to persuade Google and others to do this, so because they have to support it, they have that.
Who is going to do this? Yeah. Now, the after-sourced decryption, the cloud can do that. The cloud is doing storage for us, doing after-sourced decryption for us, but he cannot access our data.
But does he still want to do it after that? Because
maybe you have to pay a fee or something, right? Well, anyway, if the data are all encrypted, do you think the service provider will still give us the service for free? Right? Because why they give us the service for free? They cannot get any information from us. Today it's free because they are able to do data mining, which is valuable information which can sell for money, right? Good for the business. If the data all encrypted, I don't think we're going to get free storage services.
One more question. So how about quantum computing? Is this somehow sensitive of this to quantum computing, or if there is some breakthrough?
In the encryption on the ciphertext, encrypted data?
Yeah, like ABA, etc. So
yeah. Well, yeah. So if the data is encrypted, sometimes we also want to perform computation on the data, right? So that is secure computation problem, and the research, probably the biggest research breakthrough is the fully homomorphic encryption, but that system today is very, very slow. So if we use fully homomorphic encryption, you can perform in theory any computations you want to do without disclosing the data. Just perform the computation over the ciphertext. But it has an overhead of more than 1 million times. Then you perform the computation in plain text. So the common approach today, the representative example is the group by MIT. They designed this CryptDB. So it's a database, it all fully encrypted. You can still do the database query and etc. All in encrypted form with a very small overhead. It's only 10 to 20% overhead. So their approach is not using fully homomorphic encryption, but they use the homomorphic encryption. I have this data, I encrypt multiple times. One time I use additive homomorphic, another time I use multiplicative homomorphic, and maybe another one I use other techniques. So by doing this combination of different crypto techniques, they can make the system work. The system has been used by Google, by SAP, so it's one of the good successful examples on performing computation over ciphertext.